Hello, welcome back to Honors Topics in Physics. There's a demo that I could do, which is a pretty cool demonstration, where basically you take a plastic bag and put some vinegar and baking soda in it, where the vinegar would be sealed so it couldn't react initially. And what you do is you take all the air out of the bag, and then you put it on a scale and you record the reading of the scale. Then you mix up all the chemicals and the vinegar and baking soda in it, and then let it inflate because it produces a gas, carbon dioxide. And then you look at what happens to the reading on the scale. And what should happen is the reading on the scale should go down. And then the question is, why would the reading of the scale have gone down when the chemicals reacted and the bag inflated? Well, the first thing to say is that no chemicals escaped from the bag, so that's the first thing to put aside. Well, I'll just jump to it. So basically, what happened is when the bag was deflated, it wasn't displacing very much air. Okay, when you mix up the chemical reactions, the mass inside doesn't change. Chemical reactions don't change the mass of a substance; they just change what the mass compounds are. Okay, but as it reacts, it inflates and it displaces more and more air, and the more air it displaces, the greater the buoyant force acting on the bag, so it appears to weigh less, even though it still has the same mass. Okay, so anyway, so let's say a stone has a volume of 5 liters. What would the buoyant force be when it's underwater, and what will it weigh? What will it, quote unquote, what will its apparent weight be underwater? So, the first thing we have to remember is that a liter of water has a weight of 10 newtons. So when it's underwater, it's going to be displacing 5 liters of water, each of which has a weight of 10 newtons. So the buoyant force acting on it is going to be 50 newtons. 5 liters times 10 newtons per liter. So there's going to be 50 newtons of water pressure pushing it up, 50 newtons of buoyant force pushing it up. So that means it's only going to appear to weigh 50 newtons less than the 250 newtons. So its apparent weight will be 200 newtons. Okay. There's a cool little trick where you can weigh an object in and out of water, and you can figure out its density very, very easily. So let's say, hey Jill, an object weighs 15 newtons out of water, okay, meaning it has a mass of 1.5 kilograms, and when you weigh it in water, it only appears to weigh 9 newtons. What's its density? Okay, well, the first thing to do is figure out the buoyant force, and the buoyant force is the difference between the weights. So 15 minus 9, so 6 newtons. Okay, now 1 liter of water has a weight of 10 newtons, but this only displays 6 liters or 6 newtons of water, which means it was 6/10 of a liter. So now we know its volume. Okay, because 6 newtons would so try that again. 10 newtons would be 1 liter. So 6 newtons would be 0.6 liters. So that's the volume of the object. We know how much water it displaced. Okay, and then finally to calculate the density, density is equal to mass divided by volume. So the mass was 1.5 kilograms out of the water, given in here. The volume we calculated from the buoyant force was 0.6 liters. Okay, so the weight would be 2.5 kilograms per liter. Okay, so kind of a cool trick. So let's say we put a piece of foam in water. It doesn't just sit on the top of the water. It sinks into the water a little bit before floating, before just sitting there at the top. Okay, how does it know how far to sink in? How does it know to stop when it does? Okay, so let's say we take a 9 Newton object, we put it in a little bit in the water. Okay, and it only its apparent weight is only 6 newtons. We let it sink in a little bit more, okay, and its apparent weight is only is 3 newtons. And then we put it in a little bit. We let it rest on the surface of the water, okay, and its apparent weight is 0 newtons, and it's not fully submerged. Okay, so as it sinks deeper and deeper in the water, the more water it displaces, okay, and the greater the buoyant force acting on it, okay. When an object is floating, okay, well, in this case right here, okay, how much water has it displaced? Well, it's displaced 9 newtons of water, okay, because the buoyant force is 9 newtons, that means it's displaced 9 newtons of water, which is the same as the object's weight, okay. So, whoops. So an object sinks until it floats, okay, which is common sense, but, okay, when an object is floating, oh, this is not cooperating. Well, there we go. The buoyant force is equal to the weight of the object. So when an object is floating, the buoyant force is equal to the weight of the object. That's a key bit of knowledge to have in your memory banks. Okay, so as the object sinks in, the buoyant force increases because the water pressure on the bottom increases because it's getting deeper and deeper in the fluid. Okay, eventually the buoyant force cancels out the weight of the object. Okay, an object that's more dense will sink into the water more. Okay, so an object that's got a density of 0.1, which is 1/10 of the density of water, will only sink in 1/10 of the way in. Okay. An object that's 0.5 grams per cubic centimeter, or half the density of water, will sink in halfway. Okay. An object such as this plastic, which has a density of 0.9 grams per cubic centimeter, which is 0.9, and which is 90% the density of water, or 0.9 density of water, will sink in 90%. Okay. Why does it have to sink in more? Well, and if these objects are all the same size, for example, just to make the math easier, an object has to displace more water because this cube weighs more than this cube. Okay, so this one has to sink in further. Okay, and this cube, having a greater density than the wood, okay, weighs more than the wood does, so it's got to sink in and displace more water. Okay, so what does this tell you about the density of ice here? It's sank in almost all the way. So about what fraction of this thing is underwater? Looks like to be about 90% or so, maybe a little bit more. And in fact, the ice's density is 0.92, which means it's very, very close to the density of water, which means it has to displace a lot of the ice in order to, or a lot of the water in order to equal the mass of the ice cube. So this whole ice cube weighs as much as the water that's being displaced right here. So you tell there's just a little bit more volume. So anyway, so now this guy is sitting on a pool of mercury. Not exactly the most brilliant thing to do, but he's doing it nonetheless. And you can see where he's floating in this mercury, and he's not displacing that much mercury compared to his size. Okay, remember, it's not that an object has to displace an equal volume of water per se, or an equal weight of water. It has to display an equal volume, or weight of fluid of the object. So in this case, mercury is a lot more dense than water. So he's having to not having to displace near as much in order to equal his weight. Okay, so a ship is loaded with some supplies. What happens to the ship as that gets loaded on? Okay, well, the ship sinks. Okay, why does the ship sink? Okay, well, if the ship weighs more, it now has to displace a weight of water equal to the weight of the shipment that was loaded and the boat. Okay, so because it weighs more, it has to displace more fluid, so therefore it sank in more. Okay, now what happens if this ship sails from fresh water, which has a density of 1, into salt water, which has a density of 1.2? Okay, does it need to displace more or less of the water if salt water has a density of 1.2? Okay, well, since salt water is more dense, it's not going to have to displace as big of a volume of that seawater. So as it floats out into seawater, it'll actually rise a little bit. Okay, So this is something they've got to take into account when they're loading ships. If they're loading them in salt water, and it's going to have to go into fresh water, it's going to sink deeper, and that could be a problem for the ship sinking. Okay, so here we've got a huge aircraft carrier. These are pretty amazing pieces of technology. Now this ship is made of iron and weighs tons and tons. How can something that's made out of iron and concrete and all that still float? Okay, well, if this is a boat, now picture this is a boat that we've cut in half. Okay, and we're looking through the boat. So this is what's called the cross section. Okay, we see that this is the volume of iron. Okay, this skinny hull. Okay, but if we look at how much water it's displaced this huge volume of iron, or this huge volume of water. Okay, so it's displacing a volume of water much larger than the iron itself. Okay, so that's due to its shape. Okay, so concept question: if we had a bathtub just big enough to hold an aircraft carrier, okay, and the boat is placed in this big bathtub, and after the water runs out, I mean, it's just spilling out all over the neighborhood. Water's just rushing out of this thing, and when the water's settled, okay, the water that's left in the bathtub weighs less than the aircraft carrier itself. Okay, could it still float? And the answer is yes, it can still float, because it's not how much water is left in the ocean. It's not how much water is left in the bathtub. Okay, it's how much water was displaced. And remember, tons and tons of water came out of this bathtub and filled the neighborhood and all that stuff. So it would still float, because it's not the amount of water left in the ocean. It's the amount of water that's displaced. Okay, a cup is filled to the brim with water, with an overflow sitting on the scale. A piece of wood is dropped in. What happens to the reading on the scale? Okay, well, is the scale reading going to go down because water flows out? Okay, is it going to go up because we put the wood in? Okay, or is it going to stay the same? Well, the answer is it's going to stay the same, because an equal weight of water flows out. Okay, as was the wood that was dropped in. Okay, so the reading would stay the same. Okay, an ice cube is filled to the brim with water, and with a floating ice cube. What happens when the ice cube melts? Okay, does water spill out because of the extra volume here? Okay, does water level drop because the ice melted? Okay, or does it stay the same? Okay. The answer is it would stay the same. Okay. How much water has been displaced? Well, an equal amount of water is what is level with the ice cube. Okay, meaning if I took the ice cube out and I put this amount of water in, okay, the cup would remain exactly the same. Well, how much water is this displacing? Okay, it's displacing an equal amount of water to that. Well, how much is that water of this ice cube going to be when it melts? Well, the same as that. Okay, so the answer is it stays the same. So, all right. So remember from before, the buoyant force is equal to the weight of the water or fluid displaced. It's really fluid displaced, not just water. So for an object to sink, okay, for an object that just sinks, its weight is greater than the buoyant force. So how does the density connect here? Well, if an object weighs more than the fluid it's displaced, okay, then it must be more dense. Okay. For an object to float, it sinks into the liquid until the buoyant force is equal to the weight of the object. In other words, the weight of the water displaced is equal to the weight of the object itself. Okay. Now, how does a hot air balloon work? Okay. Well, so when we have a balloon that's full of air, okay. So this is kind of an interesting one. There's several different ways to explain it. I'll explain it just this way. So as we heat the air inside, it expands. What happens to the air that expands? It spills out through the bottom. Okay. So as we heat it, more and more air spills out, more and more air spills out. This thing gets lighter and lighter and lighter. Eventually, it gets less dense than the air itself, and that includes the density of the basket and everything else. So eventually it gets less dense than the air around it itself, and it floats. Okay. So go ahead and do worksheet 9-4 and do your best, and I'll see you soon.